Hello again. In this sequence of videos, we're going to examine one of the most important theorems in vector calculus, the divergence theorem. We're going to build up to our understanding of this equation through some use of physics and an understanding of how things flow through space. This video is going to rely on your understanding of vectors, of vector products, and also of the vector operator. So if you haven't looked at that, go back to the previous videos on those topics, and that will prepare you to understand what's going on in this video. So first, to understand the divergence theorem, we should talk a little bit about flow. So we want to understand what is the balance of a particular, say, a substance dissolved in a fluid that's flowing. And that will help us to understand the meaning of the divergence theorem and also the interpretation of the divergence operation. So let's consider a general volume. I'll just draw it here as all good general volumes in mathematics. It's shaped something like a potato. The potato is obviously the most general shaped object that we can think of. Nonetheless, let's say we have a potato and we have some sort of substance flowing through space around it. So we've got, I'll just draw some arrows here at random directions to represent flow of some substance through space. And I'll define the flow at any point here. Let's say at this point, the flow, or the m dot, I'm going to call that the mass flux rate. So that's a rate of flow. I'll define that as the concentration at any given point, rho, multiplied by the velocity at which it's flowing, and then multiplied by a small piece of area through which it's flowing. So concentration has units of mass per unit volume, and velocity has units of distance per time or length per time. So I'll write in here units of mass per volume, mass per length cubed for concentration. For velocity, it has units of length per time. And for a piece of area, it has units of length squared. So the units of this whole expression work out to mass per time. Now, it doesn't have to represent mass, it could represent any conserved quantity, but the important thing is that it's a rate per amount of a quantity per time. Now, to understand why that's useful, we can recognize that for any conserved quantity, looking at a volume of interest, so I'm going to call this volume here V, the balance of that substance flowing through the volume is given by this expression. We'll have the sum of the flux rates going out of the volume minus the sum of the flux rates coming into the volume, and that's equal to the time rate of change, the negative sign in front, of the substance in the volume. So this might represent the amount of mass per unit volume of a substance dissolved in a flowing fluid. If the substance of interest is, say, heat energy, it might represent an energy balance, but the point is that this is some sort of a balance. So I'm going to write mass balance, but with mass in parentheses to indicate that it could represent any conserved quantity. So we want to understand, okay, what is actually this mass balance? There's a few different ways that mass could enter or exit this volume here, this volume of interest. So one of the ways I already sort of introduced here is through a flux rate through the surface. So I have one type of mass flux rate. So I'll put this in brackets. I've got sum of mass flowing out minus sum of mass flowing in due to flow. So the substance is dissolved in the fluid and the fluid is flowing at a certain velocity. So mass can enter or exit this volume through small pieces of area. So if I draw a small piece of area here, I'm going to kind of keep up with my color convention that I've been using here. I'm going to rewrite the dA. I'm going to call it ds here. So this little piece here is ds, the area of it. Now, the question is here, how do we assess whether it's an inflow or an outflow? So if we can know what is the direction of the velocity relative to the surface that it's going through, and whether that's going into or out of the volume, we can put a positive or negative sign. In general, we don't necessarily know which direction v is relative to the area that it's going through. So what we use is something called a directed area. So I can say that the directed area here, ds, I'm going to draw a little arrow. This ds is equal to an outward pointing normal vector, so n hat. So I'll put a little sort of thicker arrow here, that's n hat. So it has unit length and it points out from the surface at that point, multiplied by the scalar area of that piece of the surface. So in general, if we've got a flow, it could be going in any arbitrary direction. So that's my rho v. And the component that is flowing on this outward direction is the only part that's actually flowing into or out of the volume. So if you remember back to our vector products, we can get the component on this direction through a dot product. So the small piece here that's flowing out, we get from taking the dot product between rho v, that flux rate, dotted with this outward normal, and then multiplied by the piece of area. And to get the total amount, so the summation over that the whole surface of our volume of interest, we're going to integrate that expression over the whole surface. So the part of the flow out, the net flow out of the volume due to the parts that are dissolved in the fluid comes from integrating this rho v dot n over the whole surface. So that is net outflow due to flow. Another way that mass can enter or exit the volume is through the generation of mass within the actual volume. So at every point within the volume, let's say in the example of a dissolved substance in a fluid, there could be chemical reactions happening in which the mass of the substance that we're tracking is either a product or a reactant in a chemical reaction, in which case it's being generated or consumed within the volume. So another component of mass flux into or out of the volume, so I'll write the same thing here again, m dot out minus m dot in from mass generation is due to a source or a sink within the volume. So one way of writing that is by calling the source, writing the source or sink per unit volume. So I could have a S, which S is a function of position and time in general. So this is per unit volume, and then I'll multiply it by a small piece of the volume. And then to get the total sum over the whole volume of interest, I'll integrate that source over the whole volume. So this is the net outflow due to sources or sinks. So those are the two ways that mass, or whatever the quantity you're interested in, can enter or exit the volume. So that's the left-hand side of this balance equation. Now looking at the right-hand side, the total mass in the volume I can get by integrating all of the small pieces of mass within the volume. And that one I can get by we already defined a concentration, a mass per unit volume. So assuming that the volume of interest stays fixed, we can get the total mass within the volume by integrating the concentration, rho, which in general is a function of position and time, over the whole volume. Now looking at the right-hand side of that expression, the dm by dt I can get by taking the derivative of this. So I'll say that's the d by dt of that integration of the small pieces of mass. And then since the only component here that's giving us mass is dv is just a small piece of the volume, then this integral I can get by taking the integral of the partial derivative of concentration with time over the whole volume. So this is the net increase of mass with time. So combining these three components here, and we can rewrite this expression now as the so mass balance again. I'll put mass in brackets. So we've got this net outflow due to the actual flow, so the concentration's moving with the fluid. We've got this integral over the surface of rho v dotted with the outward pointing normal to get the component that's actually flowing out. So parts of the flow that are moving parallel to the surface do not leave the volume, they stay inside the volume. So we're only interested in those components that are actually flowing out. So that's one part of the story of the left-hand side. Next we have the integral over the volume of any sources, say due to chemical reactions or any other source of the quantity that we're interested in within the volume. If it's energy flow or heat flow that we're interested in, this source could be, say, due to friction, the internal friction within the volume. So integral of the source term over the volume. And then on the right-hand side of our balance equation, we have the negative of this integral over the volume of d by dt of rho over the whole volume. So this is our new way of writing the mass balance sort of in more detail. It's the same expression as up there for the mass balance. So in principle, we're summing mass fluxes out minus mass fluxes in, and that's equal to the net rate of decrease of mass in the volume. So the negative sign here means the right-hand side is a net rate of decrease. So that's a starting point for our understanding of the divergence theorem. In the next video, we'll talk a little bit more about how we can take this expression a little bit further and understand its equivalence with the divergence.